Hello, I'm Doug from Group38. Today's presentation will be divided into 5 parts, as shown on screen. First is the introduction. In this task, our team designed and built an autonomous robot that mimics a biological walking mechanism using Lego to participate in a Robot Wars competition. The specific design is divided into 3 main parts. Firstly, walking ability, where the robot was required to mimic the walking behaviour of living things using legs rather than wheels or tracks. Secondly, it was required to be autonomous, where it must be able to sense its surroundings and respond autonomously without external control. And thirdly, it must have a combat capability, where the robot should have both offensive and defensive capabilities within the arena. The 5 members of our team are shown on screen. Lixin Jin was in charge of developing the robot's program. Haozu Zhu was in charge of designing and installing the weapon. I was in charge of designing the robot's structure and modelling it in CAD. Binyu Huang and Xunpeng Huang suggested modifications to the robot and assisted in the assembly of the robot. Structural design. First is the main body structure. The main body of our robot is designed with a low centre of gravity and a low height, drawing inspiration from the Ankylosaurus. The low centre of gravity makes the robot less likely to tip over, while the low height effectively avoids the opponent's range sensors and improves stealth. In addition, our strong frame structure ensures the durability of the robot during battle. Next is the sensor structure. Both sensors are arranged at the front of the robot to ensure the low centre of gravity is maintained, while avoiding interference with the rear-mounted weapon system. The ultrasound sensor is used to detect the range of the opponent, while this color sensor is used for boundary recognition.
Then there's the leg structure. In this part, we use straw motor drive by alternately controlling the positive rotation of the motors to make the legs move alternately, so as to realize a stable forward movement. At the same time, alternating the motors in the opposite direction can realize the robot's insert flexible steering.
Our weapon design is inspired by the tail attack of the dinosaur, using a gear system to enhance the swing strength and a single motor drive to control the swing left to right. The weapon can effectively attack the opponent's leg structure. In summary, our robot structure balances stability, flexibility, and aggressiveness.
Next, for the program we used, the block diagram of the program can be seen in the figure on screen. At startup, the system initializes the optical reflection sensor and the motor rotation angle measurement module, and then enters a continuous execution loop.
The robot's behaviour is based on feedback from both the sensors, with decisions based on the following conditions. If the ultrasonic sensor detects an obstacle within 30 centimetres, or the laser sensor detects reflectance below 30%, the robot will initiate an obstacle avoidance manoeuvre. If no obstacle is detected, the robot continues with its patrol program. When the robot initiates an obstacle avoidance manoeuvre, it first emits a bark as a warning. It then rotates the motors in opposing directions to turn the robot. Once the cumulative angle of rotation of motor A exceeds 800 degrees, the steering stops. The robot then moves forward slightly and the rotation angle is reset. For the conventional patrol mode, the robot will use one of 2 randomised paths, either direct patrol, where it heads directly forward, or rotary patrol, where we'll have counter-opposing rotations for each leg for 3 cycles. After this, the robot will continue to patrol forward. To counter threats from behind and enhance its bionic properties, the robot is equipped with a weaponised tail controlled by motor C, operating continuously at 60% power and swinging back and forth in a 90-degree sector. The 4th section is the results analysis. The robot was measured to have a speed of about 3 meters per second. The robot was measured to have a forward speed of about 3 centimeters per second, a steering speed of about 40 degrees per second, and a maximum weapon swing angle of 90 degrees, and a weapon swing frequency of 4 Hz. Our robot exhibited excellent walking stability due to the use of rubber tires with sufficient friction to support the feet, preventing it from slipping during movement. The speed proved to be ideal for a robot design balancing both mobility and control. There were of course shortcomings. When encountering an enemy robot, the rotation speed proved to be insufficient for fast turns, especially when faced with faster walking robots. This affected the effectiveness of the weapon system in combat. Secondly, our very low height weapon aimed to attack the lower leg structure of other robots. We achieved the desired effect in testing, but unfortunately could not in real-world combat due to the solid opponent legs. Finally, the edges of the arena had some unexpected impacts on the robot. During swinging, the weapon often got caught on the warped edges of the arena and the tape. This affected the robot's movement and caused disruptions to the robot's steering process.
To enhance robot performance, we decided first one, increasing the real weapon's height to prevent paper edge jamming. Second one, optimizing weapon sensor interaction with conditional logic for improved combat responsiveness. Thank you very much for listening.